Hello, my name is Ilge Akkaya. I'm a graduate student working with Edward Lee, and I'm a part of TerraSwarm. Today I'll be talking about Pilot, which is an actor-oriented toolkit we're developing for swarm applications. So as the Internet of Things become more and more widely deployed, not only the volume of the data is increasing, but also the nature of the data is changing. So traditional machine learning and big data applications are designed to operate on big historical static data. But now we have streaming data from the Internet of Things, and it's real time, and it's coming from sources in a streaming manner. So the research question we're addressing is that, are there better programming formalisms than using imperative code that can exploit the streaming nature of the data, as well as provide a composable interface for designing these big data applications for the swarm? I'd like to introduce Ptolemy at this point. Ptolemy 2 is an open source platform for modeling and design of systems. It is developed here at Berkeley, and it's an actor-oriented language that enables design of hierarchical composition of different models of computation. Following the advancements in the IoT, Ptolemy recently introduced accessors, which are actors that provide access not only to other actors, but to physical sensors, actuators, and remote services that we have. An actor in Ptolemy has input ports, output ports, and an input representation, as opposed to object-oriented models where you have function calls interacting with objects. For an actor-oriented language, you would have data flowing through an actor model. And Pilot is the learning and optimization toolkit that is built upon Ptolemy. It is actor-oriented, and currently we're building Bayesian inference, state estimation, and optimization models that are operating especially on streaming data. So I'd like to move on to the applications we've considered. One wide family of applications we're designing are robotic sensor networks, in which different actors need to communicate to each other to perform a common task. One example of this is model predictive control in a multi-objective way. So in this example, two robots are trying to reach a target while avoiding obstacles, whose locations are estimated on the fly as the robots are moving. And another application that we're considering are cooperative mobile target localization, where we have a team of robots which are trying to localize a mobile target as well as to approach it. And the trajectories, the paths of the robots are being planned collaboratively on the fly. Another family of applications are automotive systems in a closed-loop manner. We're trying to receive telemetry data from a vehicle, build a model of the driver behavior, and if the driver is performing an aggressive act, we're trying to inform the driver in a closed-loop manner. So we run Pilot as a cloud application which learns a Bayesian model based on the style of the driver received by the telemetry data, and we inform the driver in real time if there's a violation. Final application I will mention is reactive jazz improvisation. For this one, we are using Pilots on streaming music data, where we're building a Bayesian probabilistic model on the fly, trying to capture the properties of the melody and then improvising along as we go. So here is a little snippet of the training melody. Pilot is listening, building the model, and then starts playing along. All right. Thank you for listening. For more details and more information, please visit our poster session in Corey Hall following this section. Thanks.